This video is intended to teach the basics of radar technology and provide basic knowledge and background on the radar principle. It is a prepared lesson on the subject of radar basics, compiled on the basis of the internet presentation www.radartutorial.eu. The radar principle had models in nature. Bats can orient themselves in complete darkness with the help of ultrasonic signals. They send a short sound pulse, a ping, and listen for its echoes. The speed of sound in the air is about 333 meters per second. This constant propagation speed allows them to measure distance of the reflecting object by runtime. Bats feed on insects, especially moths. Even such small objects are unerringly located by runtime measurement and stereophonic hearing with the two oversized ears. Dolphins use the same principle for hunting. Underwater, sound propagates much faster and with less loss than in the air. In seawater, the speed of sound is about 1,500 meters per second. Therefore, using this principle, dolphins can search a much larger area for prey, often more than 100 meters, than would be possible underwater with purely optical vision of only a few meters. A technical device exploiting this functional principle for locating submarines was registered as a patent in 1931. Much later, these devices were called active sonars. Just 2 years later, the same operating principle was applied and patented using electromagnetic waves instead of sound waves. All previous radar inventions did not really deal with the time of flight measurement yet. The electronic principle of radar sets works similarly to the echo of a sound wave observed in acoustics. A probing signal is transmitted, and a distance is calculated from the runtime of the echo signal received back. There are three basic physical laws that govern the operation of any radar set. The reflection of electromagnetic waves. When electromagnetic waves hit an electrically conductive surface, they are reflected. If the reflected wave is registered again at the point of origin, as an echo, this is evidence that there is an obstacle in the direction of propagation. The constant propagation speed of the electromagnetic waves. The electromagnetic waves propagate with speed of light, approximately 3 times 10 to the 8th power, meters per second. Due to this constant propagation speed, the distance of reflecting objects, airplanes, ships, and vehicles, can be determined exactly by measuring the runtime of the pulses. The straight-line propagation of the electromagnetic waves. The propagation of the electromagnetic waves in the frequency range of radar sets is assumed to be straight-line propagation. By special antennas, the electromagnetic waves can be bundled in a certain direction. Thus, it is possible to determine the angular coordinates, bearing angle and elevation angle. If a time measurement is made at the point of origin from the beginning of the emission of a high-frequency pulse until the arrival of the reflection, the distance between the point of origin and the obstacle can be calculated. If the waves are strongly directionally bundled, the direction in which the object is located can also be determined. With the values of distance and direction, the position of the object in relation to the point of origin can be determined unambiguously. Devices that use electromagnetic waves to determine the position of objects are called radar. This is an artificial word originating from radio detection and ranging. This term refers to electronic devices that can detect the existence of electromagnetic waves from reflective objects and measure their distance, direction, and often altitude, course, and speed. Since electromagnetic waves propagate even in darkness and can penetrate fog or clouds almost unimpeded, a radar set can determine the position of aircraft. Ships are simply obstacles even when these objects are invisible to the human eye due to excessive distance, bad weather, or darkness. Modern radar sets can usually extract much more information from the echo signal of a target. However, calculating a range based on a runtime measurement is the most important feature of a radar set. However, the reflection at the target is not a mirror reflection, but rather a scattering of the transmitted signal in all directions. So, the receiving antenna does not necessarily have to be at the same location as the transmitting antenna. With bistatic radar sets, there is a wider distance between the transmitter and receiver, which has the advantage that the transmitter can have a higher transmit power without the risk of destroying the sensitive receiver right next to it. In addition, some stealth bomber measures are not completely ineffective with bistatic radar sets, but they are ineffective. The disadvantage is that synchronization between the transmitter and receiver is more difficult, and the runtimes on the line between the transmitter and receiver must also be considered when calculating the target range. Monostatic radar sets either have the transmitting antenna right next to or above the receiving antenna, or they use only a single antenna for simultaneous transmission and reception from the outset. The distance measurement of a radar can be shown on a simple oscilloscope. At the screen, a luminous dot moves synchronously with the transmitting pulse and leaves a trace. The deflection starts when the transmitting pulse leaves the antenna. The luminous spot moves to scale on the oscilloscope with the electromagnetic wave in space. When the antenna receives the echo pulse, this pulse is also displayed on the oscilloscope. The distance between these two pulses is now a measure of the distance of the aircraft and can be measured directly on the oscilloscope in kilometers. The distance is determined from the runtime of the high-frequency transmitted signal and the propagation speed, the speed of light, c0. The measured runtime is directly proportional to the distance. Actually, an oblique range is measured, the distance between the radar set and a flight target with a flight altitude usually far above the altitude of the radar antenna. However, if the measurement error is small compared to the measured distance, you can ignore it. What scale the oscilloscope uses is usually unknown to the user. It depends on the speed of the horizontal deflection of the electron beam. Therefore, scale marks are often inserted, for example, pointing downwards from the deflection line. If these pulses are to display at 10 km grid, then the clock frequency of these scale marks is 15 kHz. The user must estimate the position of every point between these marks. In modern computerized displays, this happens similarly, except that the clock for the scale is much higher. It is often in the megahertz range to get more accurate results. At 15 MHz, the distance resolution of the display would be 10 meters. However, an analog oscilloscope displays these pulses as a voltage sum. Thus, the first scale mark slips onto the pulse roof of the fixed target echo. For the runtime measurement, the way there and the return path of the propagating electromagnetic wave must be considered. Therefore, for monostatic radar sets, the product of the propagation speed, here, the speed of light, c0, and the measured runtime, t, must be halved. Due to the very high propagation speed, the reasonable range of values of the expected runtime is often very small. 1 microsecond corresponds to 150 meters. This speed sets high demands on the accuracy of clock frequencies and bandwidths of filters and amplifiers. It is useful to remember this ratio because, with this auxiliary constant, it is easy to convert a distance into a runtime and vice versa. A determination of the side and height angle of the target is possible by the bundling of the transmitted and received energy by the antenna. The angle measurement is made possible by the fact that the antenna must point exactly in the direction from which it receives the echo signal. These angles can be measured as elevation and bearing angles at the antenna turntable. The full turn corresponds to an angle of 360 degrees. The counting direction is mostly clockwise. Exceptions may be older radar sets used as directors for artillery guns. For stationary radar sets, the origin of the count corresponds to the geographic north. For moving radar sets, the count may also be based on the course of the ship or aircraft. Bearing angles are transmitted by angular transmission from the antenna to the display unit or the computer. Older systems use rotary encoders and servo motors, while newer systems use encoders that divide the full circle of 360 degrees into up to 2 to the power of 14 equals 16,384 individual steps. This corresponds to an accuracy of 0.022 degrees. Two-dimensional measuring radar sets can only measure the distance and one bearing angle. The antenna pattern is very narrow in the bearing angle, in the range of 0.5 to 10 degrees, but very wide in the elevation angle, in the range of 30 to 70 degrees, so that all missiles are detected in this one bearing angle. Three-dimensional measuring radar sets divide the antenna pattern into narrow sections and measure the distance individually within these sections. Thus, an elevation angle is measured. The height can be calculated from the target distance and the elevation angle. Certain design-specified performance standards of radar sets are: carrier frequency. The carrier frequency is the frequency at which the radio frequency energy is generated. The principal factors influencing the selection of the carrier frequency are the desired directivity and the generation and reception of the necessary microwave radio frequency energy. For the determination of direction and for the concentration of the transmitted energy so that a greater portion of it is useful, the antenna should be highly directive. The higher the carrier frequency, the shorter the wavelength, and hence the smaller the antenna required for a given sharpness of the pattern of radiated energy. Pulse repetition frequency. The pulse repetition frequency, PRF, is the number of pulses transmitted per second. Some characteristic values may be 360, 1000, 1500, 2200, and 3000 pulses per second. The majority of modern radars operate within a range of 300 to 4000 pulses per second. Pulse length. Pulse length is defined as the duration of the transmitted radar pulse and is usually measured in microseconds. The minimum range at which a target can be detected is determined largely by the pulse length. Peak power. The useful power of the transmitter is contained in the radiated pulses and is called the peak power of the system. High peak power is desirable to produce a strong echo signal over the maximum range of the equipment. The peak power that can be developed is dependent upon the interrelation between peak and average power, pulse length, pulse repetition time, or duty cycle. Average power. Low average power enables the transmitter tubes and circuit components to be made smaller and more compact. Duty cycle. The peak power that can be achieved depends on the correlation between pulse power and average power, the pulse length and the pulse repetition time, or duty cycle. The maximum unambiguous range is the longest range to which a transmitted pulse can travel out to and back again between consecutive transmitted pulses. In other words, the maximum unambiguous range is the maximum distance during which radar energy can travel round-trip between pulses and still produce reliable information. If a target is so close to the transmitter that the echo is returned to the receiver before the transmission stops, the reception of the echo, obviously, will be masked by the transmitted pulse. For example, a radar set having a pulse length of 1 microsecond will have a minimum range of 164 yards, or 150 meters. This means that the echo of a target within this range will not be seen on the radarscope because of it is masked by the transmitted pulse. Resolving power is the capacity of radar to resolve two objects that are close together. A distinction is made between radial resolution, the range resolution, which depends on the transmit pulse duration or the transmit pulse bandwidth, and lateral and elevation angular resolution as parameters of the antenna. There are several ways to divide the frequencies into radar bands. Currently still in use is the historical division of the Institute of Electrical and Electronics Engineers. It was created by distributing initial letters, each derived from a keyword characterizing the frequency range. High frequency band, very high frequency band, and ultra-high frequency band were adopted from broadcast frequencies and contain the term frequency in their names, after which they are subdivided only according to wavelength. L for large wavelength, S for short wavelength, C for compromise between S and X, X for unknown, also a frequency to be kept strictly secret. K for Kurz, short wavelength in German, later again subdivided into Ku for Kurz unten, below the K band in German. Ka for above K band. The NATO designations were derived from the requirements of electronic reconnaissance and countermeasures. There the classifications were made according to the changed characteristics and consequently in the differently usable hardware. The two different classifications are rather confusing. With a jammer working in the D band, a radar set in the L band is jammed and not in the D band. However, radar sets also belong to the electronic reconnaissance, which is why the classification of the IEEE seems somewhat antiquated. Above all, the arbitrary letter distributions above 100 GHz are somewhat strange and originate from company internal designations, which were taken over depending upon lobby by the IEEE. The pulse repetition frequency, PRF, is the number of pulses transmitted per second. The radar set transmits a short high-frequency pulse with the transmission pulse duration tau and waits for the echo signals between the transmission pulses. The time from the beginning of one transmitter pulse to the beginning of the next pulse is called pulse repetition time, PRT, or pulse repetition period, PRP. Both terms are the reciprocal of the pulse repetition frequency. Receive time. The time between the transmission pulses is generally the reception time. The reception time is always shorter than the difference between the pulse repetition period and the transmitter pulse width, and it is sometimes additionally limited by a so-called dead time in which the receiver is switched off shortly before the next transmission pulse. With some radar sets, there is a short recovery time between the transmit pulse and the receive time. This recovery time occurs when the duplexer switches off the receiver because the transmitting power is too high. However, if the transmitting power is low, the receiver may be in working order during the transmitting pulse. In this case, the reception time includes the transmission time. Dead time. A dead time can be inserted between the end of the receiving time and the next transmitting pulse. Generally, system tests are performed on modern radar sets during the dead time. Radar sets using a phased array antenna urgently need such dead time. During this time, the phase shifters of the antenna are to be reprogrammed for the next direction of the antenna pattern. This procedure can take up to 200 microseconds. Therefore, the dead time requires large values compared to the receiving time. The transmitter's pulse determines not only the range of a classical radar but also the range resolution. Therefore, it should be as large as possible, for good range, but as short as possible, for good range resolution. These two requirements can usually only be realized with high-performance transmitter tubes, magnetrons, klystrons, or traveling wave tubes. The duty cycle, D, is the ratio of the pulse duration to the pulse period and the ratio of pulse power to average power. Formally, the impulse power is not of such essential importance, but rather the energy contained in the pulse. Power is energy per time unit. If we assume that the echo pulse has the same duration as the transmitting pulse, the ratio of the powers is equal to the ratio of the energy quantities. Now, power is easier to measure than energy quantities, which is why the transmit power is used as the basis of calculations for radar. The power supply must provide only slightly more than the average power. The average power is usually stored in capacitors or delay lines. These components are discharged during the short transmission pulse length. A continuous wave radar will achieve the same range with the energy in the average power as the classical pulse radar with its energy during the pulse power. The maximum unambiguous range, Rmax, is the longest range to which a transmitted pulse can travel out to and back again between consecutive transmitted pulses. In other words, the maximum unambiguous range is the largest distance radar energy can travel round-trip between pulses and still produce reliable information. If this is not the case, the echo signal slips into the next following receiving time and is then displayed in the wrong distance. The radar cannot easily decide from which pulse period the echo signal originates. The distance measurement is ambiguous. Such a measurement is also called folded range. The relationship between the pulse repetition frequency or their reciprocal value pulse repetition time, the capital letter T, with the needed delay or runtime determines the unambiguous range of the radar. In this equation, the transmit pulse duration, tau, expresses that the entire echo signal must be received before a target sign can be generated. If the transmit pulse duration, tau, is very small compared to the pulse following period, it can be ignored with sufficient accuracy. One possibility to avoid ambiguous measurement results is to code successive transmit pulses differently so that the radar signal processor can assign the correct transmit pulse. Another possibility is to suppress such wrongly presented echoes with a staggered pulse repetition period. Examples are known where only two different pulse periods are used alternatively, but up to 8-fold interleaving is commonly used. In magnetron transmitters, one must ensure that such interleaving allows a uniform average power. A very long pulse period must be followed by a very short one. Now, the position of the ambiguous echo signal in the following pulse period is no longer stable. Instead of a small bright arc on the screen, a cloud of dots appears, and the operator can see that this cloud cannot be a target. A modern radar signal processor can properly combine these dots and then display the target at a proper distance. This process is called unfolding. Radar sets that use a shared antenna for transmission and receiving with a duplexer usually also have a minimum possible range. This results from the fact that with high transmitting power, the receiver must be switched off during the transmitting time. The minimum range is the minimum distance from the antenna that a target must be to be detected. For this, it is necessary that the transmit pulse has completely left the antenna and the radar set has switched to receive. The transmission time tau should, therefore, be as short as possible if targets are to be detected in close range. The switching time of the duplexer is also included in the formula as switching time or recovery time. Air surveillance radars at airfields therefore use two different pulse lengths. A very short pulse for the close range with 1 microsecond length, and a longer one for the long range with 64 microseconds length. Both pulses use the same pulse power, but the short pulse contains much less energy. More energy would also not be necessary for the close range. Sometimes, this limitation is omitted if the radar uses only low transmit powers and then uses a ferrite circulator as a duplexer. This is also true for active phased array antennas because, although a large total transmit power is generated, the individual active antenna elements each apply a small portion of the power only. Another possibility for the occurrence of the minimum possible range is when the radar antenna is located on an elevated site and cannot radiate directly downward. Therefore, a blind spot arises, and on the surface, there is a range of distance that cannot be monitored. This case occurs with coastal surveillance radars and naval navigation radars mostly. Radar accuracy is the degree of conformance between an estimated or measured position and/or the velocity of a target at a given time and its true position or velocity. Radar accuracy is usually presented as a statistical measure of system error. With a pulse radar, the runtime is generally measured from the rising edge of the transmit pulse to the rising edge of the echo signal. The accuracy of this measurement depends on the magnitude of the clock frequency for this time measurement. Measurement results between the cycles aren't possible and generate a systematic measurement error. The accuracy depends also on the size of the individual range cells in signal processing. A random error occurs with a pulse radar when the rising edge of the echo signal is distorted by noise. Since the pulse is always superimposed with noise during measurement and the pulse plus the noise is measured as amplitude, the pulse is displayed bigger than it is. This noise shifts the pulse edge upwards and causes a measurement error in the runtime measurement. The accuracy of the angle measurement depends both on internal signal processing methods and on external conditions. Anomalous propagation conditions, which frequently occur due to changes in air pressure in height angle measurements, can principally also occur in bearing angles and form a random error. However, more frequent systematic error sources have internal causes. Range resolution is the ability of a radar system to distinguish between two or more targets on the same bearing but at different ranges. The degree of range resolution depends on the width of the transmitted pulse, the types and sizes of targets, and the efficiency of the receiver and indicator. Pulse width is the primary factor in range resolution. The transmitting pulse takes a dimension of C0 multiplicated with tau I in free space. A 1 microsecond long pulse distributes its energy over a length of about 300 meters in the main radiation direction of the antenna. If two reflecting objects are within this distance, their echo signals run into each other until they merge into a single, but now somewhat larger, pulse. Here, the radar can no longer distinguish whether it represents a target for two reflecting objects or one larger object. Ideally, the transmit pulse is rectangular. However, due to the receiver bandwidth, it is less sharpened and resembles a Gaussian bell curve. Two of these closely spaced curves can be identified as two objects if the pulse maximum of the second pulse is located outside the zero of the first pulse. Then, a significant local minimum appears on the impulse roof, which proves that there must be two targets. In this animation, a 1 microsecond long transmitting pulse will hit two airplanes, which are only a little more apart than the 300 meters length of the bundle of electromagnetic waves. Nevertheless, their echo signals are separated. Both echo signals would flow into each other if the distance is smaller than 150 meters, that is, smaller than half the length of the bundle. Note that here, the length of the impulse in the space is not divided into outward and return paths. Therefore, the 1 microsecond still corresponds to 300 meters. Here, the animation shows the case with a smaller distance than 150 meters. The radial range resolution is the limiting case where two echo signals are separated and processed as two target echoes. The minimum target distance SR, from spacing radial, results from the values speed of light, C0, pulse duration, tau, and the factor 1/2 for the way and the way back. Note: with a classical pulse radar, the range resolution depends on the transmission pulse duration. Radar angular resolution is the minimum distance between two equally large targets at the same range which radar can distinguish and separate from each other. The angular resolution is a function of antenna parameters. It can be given directly as an angle or as a lateral distance between aircraft measured as a function of distance. The angular resolution characteristics of radar are determined by the antenna's half-power beamwidth, which is defined by the -3 decibels points. The half-power points of the antenna radiation pattern are normally specified as the limits of the antenna beamwidth for the purpose of defining angular resolution. Two identical targets at the same distance are, therefore, resolved in angle if they are separated by more than the half-power beamwidth of the antenna. The angular resolution as a distance between two targets may be calculated by trigonometric equation. However, very modern radar sets can still distinguish between one or two targets even if both are flying directly next to each other. Then known radar signatures are evaluated, this is, all changes of the echo signal compared to the transmitted signal, like a fingerprint. This can include, for example, changes in Doppler frequencies caused by so-called jet engine modulation. This is, Doppler frequencies caused by the rotation of the compressor blades in the turbines. The number of engines can thus be determined and plausibility with the other data can be established. The resolution cell, or pulse resolution volume, characterize the joint resolving capability according to the range and angular coordinates. Usually, the resolution cell is assumed to be limited by the half-power beamwidth theta of the antenna directivity pattern and the length of the pulse in free space, with tau as the duration of the transmit pulse, or, in the case of intra-pulse modulation, by the duration of the signal at the output of the pulse compression device. In the case of a very narrow pencil beam, this means, with small values of the angles theta azimuth and theta elevation, the size of the volume of the resolution cell can be calculated according to the following equation. The restriction, small angles, in this equation results from the approximation that can be assumed that the sine of a small angle is equal to the angle in radians. When these angles are given in degrees, they should be converted to radians by multiplying by pi divided by 180. In weather radar, the resolution cell has greater significance. Since the volume of the resolution cell increases with increasing distance, many more raindrops will now fit into it for the same rain intensity. The radar cross-section will thus also increase. This increase affects the maximum range of a weather radar. Because of this, reflecting objects in weather radar are also referred to as a volume target. The volume target fills the resolution cell. In contrast, surveillance radars usually detect point targets. The reflecting object gets lost in the increasing volume with increasing distance. A comparable significance for a surveillance radar arises when the resolution cell is filled with passive interference. This case can occur with the so-called chaff. Chaff is artificially deployed clouds of small dipoles, which slowly sink to the ground and generate an area of strong echo signals, behind which attack aircraft can hide. However, weather interference can also occur at higher frequencies. For example, a mobile speed camera will not work in heavy rain. But there are other methods of speed measurement than just radar. The processes in an all-round searching pulse radar are time-dependent. This context results in special technical terms such as dwell time and hits per scan. The dwell time of a 2D omnidirectional radar depends mainly on the half-power beamwidth theta azimuth of the antenna and the rotational speed of the antenna. The calculation formula is: during this dwell time, the pulse radar sends out several transmission pulses. The target is, therefore, hit by several transmission pulses. The hit number, m, indicates how many echo signals are generated per target during each antenna slew, or rotation. For example, for an all-around search radar, the hit number represents the number of echoes per antenna rotation. The number of hits per scan is determined by the dwell time and the pulse repetition period. To enable radar systems to evaluate the target information with sufficient accuracy, hit numbers of 1 to 20 are necessary. This number depends on the working principle of the radar system. A monopulse radar can process 1 hit per scan but needs up to 3 hits for Doppler processing. An air traffic control radar using the sliding window method for bearing angle determination requires about 18 hits. Many radar sets use pulse integration in radar signal processing to distinguish target signs from noise and interference pulses. If the number of hits is too low, this target sign can be lost by the increased threshold values due to the interference. Radar parameters such as antenna rotations per minute, dwell time, maximum unambiguous range, pulse repetition frequency, PRF, and the maximum number of hits per target are strongly interdependent. Finally, all other radar characteristics, such as range and azimuth resolution, blind speed, etc., could be derived from these basic timing considerations. A classic radar that didn't use monopulse technology, operating as an air traffic control radar, needs a data renewal time of fewer than 5 seconds. Therefore, the antenna must rotate with slightly more than 12 revolutions per minute. This requirement limits the receiving time and the maximum unambiguous range as follows. These 5 seconds are divided by the ratio of the half-power beamwidth of the antenna to determine the dwell time. If the half-power beamwidth is given with 1 degree, the 5 seconds must be divided by 360, which results in about 13.8 milliseconds in this example. This dwell time is divided by the number of hits per scan required in the radar signal processing, example given, by 18 hits, which results in 771 microseconds. Therefore, the pulse repetition period must be less than or equal to 771 microseconds, which sets the pulse repetition frequency at less than 1.2 kHz. We now continue to calculate with the value of 1 kHz. These 771 microseconds also correspond to a maximum unambiguous range of 115 kilometers. In practice, less than 771 microseconds because a maybe necessary dead time was not considered yet. In practice, air traffic control radars at airfields have a maximum range of only 110 kilometers. This result corresponds to about 60 nautical miles. Another example, but now the other way round. For a maritime navigation radar, the maximum range is limited by the curvature of the Earth to about 40 nautical miles. A nautical mile is defined as 1,852 kilometers. 40 nautical miles, therefore, corresponds to about 74 kilometers. All other radar parameters are now adjusted to this maximum range, such as transmit pulse power, pulse repetition frequency, and antenna rotation speed. Here, the maximum receiving time for an unambiguous range measurement is about 74 divided by 0.15, which is nearly 494 microseconds, and the pulse repetition frequency is a reciprocal of 494 microseconds, which is equal to 2 kHz. For hits per scan of perhaps 20, an illumination time of 9.87 milliseconds is required. If the radar antenna has a half-power beamwidth of 5 degrees, the full circle can be divided with 360 divided by 5 equals 72 sectors. 9.87 milliseconds times 72 gives 0.71 seconds for one antenna rotation. Most of these maritime navigation radars rotate their antenna with 60 revolutions per minute, i.e., 1 revolution per second. This value is quite sufficient for this time budget. The calculation of the necessary transmit power is shown in the video about the radar range equation. This time budget explains some ways to get around the maximum range limitations. One possibility is to reduce the necessary hits per scan. Consequently, this measure leads to a monopulse radar, which means a higher circuitry effort. In surveillance radar, overreaches may be suppressed, but these overreaches can be exploited selectively with satellite radar. At an orbit altitude of 800 kilometers, echo signals from the Earth's surface are expected at most from distances of 780 to 820 kilometers. The remaining distances are predominantly anechoic. Thus, satellite-based radars for Earth observation use a very high pulse repetition frequency sufficient for a non-ambiguous range of 40 kilometers. The radar can then computationally add the time of the empty pulse periods to calculate the runtime for about 800 kilometers. For adjacent points on the Earth's surface, a jump in the measured distance of 40 kilometers difference is unlikely. This mode of operation is called high PRF mode. With a different internal modulation of the transmit pulses, echo signals can be assigned to the corresponding transmit pulse. This means that a runtime greater than the pulse period can also be detected. With multi-function radars, even different tasks can take place simultaneously. For example, a strongly focused pattern can be transmitted to track a ballistic missile, and while waiting for the echo signal, other pulses can be transmitted for surface search. With the digital shaping of virtual antenna patterns, various virtual directional patterns can be generated in memory, which then determine the direction of reception of various echo signals. The use of respective coded transmit pulse makes runtime and distance measurable. You might also visit the radar tutorial on the internet. It is easy to find, use the keyword radar basics, and no matter which search engine you use, it will be listed first in the results. Thank you for your attention.